Good morning, everyone. Today we're going to discuss about the wave-particle duality. But before that, let us first read the learning objectives. At the end of the lesson, the student shall be able to explain the concept of wave-particle duality, discuss the key experiments and scientists who contributed to the understanding and acceptance of wave-particle duality, provide examples of experiments that demonstrate the wave-like behavior of particles and the particle-like behavior of waves. And lastly, determine the application of wave-particle duality in different fields. The dual nature of light, an exploration of wave-particle duality. Now, what is light? Light or visible light is electromagnetic radiation that can be perceived by the human eye. It is a fundamental part of our world, and its nature has puzzled scientists for centuries. In this presentation, we will explore the wave-particle duality of light, which has revolutionized our understanding of the universe. Wave-particle duality is a fundamental concept in quantum mechanics that describes the behavior of matter and energy. It is the idea that particles can exhibit both wave-like and particle-like properties, depending on how they are observed or measured. So wave-particle duality was proposed by Louis de Broglie in 1924 and later confirmed by experiments such as the double-slit experiment. It challenged the classical view that particles were discrete, localized objects and instead suggested they had wave-like properties. So in wave-like properties, particles exhibit wave-like properties such as interference and diffraction. Interference occurs when waves overlap and create a pattern of alternating bright and dark regions. Diffraction occurs when waves bend around obstacles and create a pattern of spreading out. On the other hand, in particle-like properties, particles exhibit particle-like properties such as position and momentum. Position is the location of a particle in space, while momentum is the product of its mass and velocity. These properties are related through the Heisenberg uncertainty principle. So what are the experimental evidence for wave-particle duality? There is a wealth of experimental evidence for wave-particle duality, including the double-slit experiment, the photoelectric effect, and the quantum scattering. These experiments have confirmed the wave-like and particle-like behavior of light and matter, and have led to our current understanding of quantum mechanics. One of the most pivotal experimental demonstrations of wave-particle duality is Tumang Yang's double-slit experiment, conducted in the early 19th century. The double-slit experiment is a classic experiment that demonstrates wave-particle duality. In this experiment, a beam of light is shown through two slits and produces an interference pattern on a screen behind the slits. This pattern is only possible if light behaves as a wave. However, when a detector is placed at one of the slits, the interference pattern disappears, indicating that light behaves as a particle. The uncertainty principle proposed by Werner Heisenberg. It is a fundamental principle of quantum mechanics that arises from wave-particle duality. It states that the more precisely the position of a particle is known, the less precisely its momentum can be known, and vice versa. This principle places fundamental limits on the precision with which certain properties of particles can be measured. So next is the Bohr model of the atom, proposed by Niels Bohr. It is a model that explains the behavior of electrons in an atom based on wave-particle duality. In this model, electrons are described as both particles and waves, and their energy levels are quantized. The Bohr model was the first successful attempt to explain the spectrum of hydrogen and remains an important concept in quantum mechanics. Now, let's proceed to the interpretation of quantum mechanics. First is the many-worlds interpretation. It is an alternative interpretation of quantum mechanics that suggests that every possible outcome of a measurement actually occurs in a separate universe. This interpretation avoids the need for wave function collapse and is still a topic of ongoing debate. Another one is the Copenhagen interpretation. It is the most widely accepted interpretation of quantum mechanics. It was developed by Niels Bohr and his colleague in the 1920s and is based on wave-particle duality. The Copenhagen interpretation states that particles do not have definite properties until they are observed or measured. This interpretation suggests that act of observation or measurement affects the behavior of particles. So what is quantum entanglement? So it is a phenomenon that arises from wave-particle duality. It occurs when two particles become entangled, meaning that their properties are correlated in such a way that the one properties of one particles are dependent on the properties of the other, regardless of the distance between them. This phenomenon has been demonstrated through various experiments and has important implications for quantum computing and cryptography. Now, let's move on the application of wave-particle duality. So, wave-particle duality has important application in many fields, including quantum computing, cryptography, and medicine. For example, quantum computers use the wave-like behavior of particles to perform calculations that are impossible with classical computers. In medicine, electron microscope uses the wave-like behavior of electron to image biological structure at high resolution. So wave-particle duality can be observed also in many real-world examples, such as rainbows, music, and sunsets. This example demonstrates the wave-like properties of light and sound that we experience in our daily lives. So what will be the future direction of wave-particle duality and quantum mechanics? The study of wave-particle duality and quantum mechanics is an active area of research with many directions for future exploration. These include the development of new quantum technologies, the search for new particles and phenomena, and the refinement of our understanding of the fundamental nature of reality. So in conclusion, wave-particle duality is a fundamental concept in quantum mechanics that describes the behavior of particles as both waves and particles. This concept has been confirmed through various experiments and has important application in many fields. However, there are still many challenges and controversies in the field of quantum mechanics, highlighting the ongoing need for research and exploration. So that's all for today. I hope you learned something. Thank you for listening.